Hello, friends. So, today we're going to start about a topic which is at the heart of mechanics. So, this topic um, is going to be fundamental with respect to how we approach any question in mechanics, right? So, when we start with kinematics, we study the one particle motion. So, we start typically with the motion of an object in a straight line, right? And after that, we go ahead and we study the motion of uh, object in a circular motion. Later on, once we go into rotational mechanics, we study the motion of an object in various kinds of rotational motion. What is common to all such motion? So, this is presented by Irodov in his Fundamentals of Mechanics book. Many are aware of the book called Problems in General Physics by I.A. Irodov, but at the same time, very few are aware of this book, which is also written by Irodov, where he presents the theory behind the mechanics and how to approach any question. So he describes in this book there are three basic ways of describe of a mo- of understanding motion. First method is a vectorial method. Second one is by using coordinates, and the third one is a natural method. Let's discuss these things one by one. What is a vector method? Vector method is just defining the position of a particle. Let's say you have a particle that's moving. So defining the position vector of a particle in space and seeing how it is changing, and with respect to the change in this vector, we define the instantaneous velocity, which is given as the change in the position vector by time. Correct? So at an instant, if you are defining that vector, it's called the instantaneous velocity vector. Now the second one, which is the coordinate system way of representing. The second one involves defining certain coordinates. Typically, we use the rectangular coordinate system. So we define the three coordinates with respect to any point in space. So that is x of t, y of t, and z of t. And then we respectively define the velocities along these respective axes, the x direction, y direction, and the z direction. Like you can see here, if I know x of t, that is the particle's coordinate in the x-axis, you could define something called as dx by dt, which would be the velocity of the particle in the x direction. Similarly, if I know y of t, which is the particle's position in the y direction, I could define the y velocity as dvy by dt. That would be my dy by dt. That would be my velocity in the y direction vy. Similarly, dz by dt would be my velocity of this particle in the z direction vz. Now, once I define this vx, vy and vz, all I have to do is I have to add them vectorially in order to get my final velocity v bar, or which is the axial velocity of the particle. So, in a sense, the particle that is moving will move with the same velocity vector v bar. The method 1 or the method 2 is just our way of understanding and representing its motion. And similarly, in the same lines, we have a third method. And this method, in this method, if you know the path of the particle, then you define the velocity of the particle in the tangential direction all the time. And at the same time, so we define a direction tangential to the path. Once we know that at every given point the particle's velocity is along the tangent, since we know the path, we will know the tangential vector as well. Therefore, this method can be employed only if we know the particle's path in advance. We should be knowing how the particle would be traveling, and then we can decide at each and every point the particle's velocity vector. So this v of here v tau represents the tangential direction, and v tau of t is the velocity of the particle at any given point. So as we can see, v tau is therefore going to be the dl by dt, which is the length, the length covered by it with time, the rate of change of the length covered with time. That is my v tau. So therefore I could say my v tau should be the magnitude of the velocity, which would be equal to dl by dt, right? So if I want the acceleration, that should be dv by dt, which would be dv tau by dt. And if you do that, we will be, since v tau, tau is a vector, v tau here is a magnitude. When I do this dv by dt, I'll have to use the product rule and do this dv tau by dt into tau, which is the direction, essentially the tangential vector direction. So therefore, plus the second term should be v tau into d tau by dt. So what would be the rate of change of the tangential vector d tau? Let's see that. You can see if any given arc going from 1 to 2, if tau 1 is the tangential direction, tau 2 is the tangential second tangential direction, d tau by dt would be like this, isn't it? Uh, the change in tau 2 minus tau 1, so that would be d tau. So d tau divided by dt. Now what I could do is, I could in place of d tau by dt, I could always define d tau by dl times dl by dt. I could just multiply and divide the numerator and denominator with dl. In doing that, my d tau by dl into dl by dt. dl by dt is a value v tau, isn't it? We already have seen it earlier that v tau is dl by dt, which is the rate of change of the the length of the arc here. So v tau square times d tau by dl. What is d tau by dl? If you look here, this value d tau and the angle alpha d alpha here, which is essentially the change in the angular, the radial positional vector d alpha, that would be the same thing here as well, d alpha. So therefore tan of, if I have to define d tau by dl, as you can see, tan alpha will be equal to d tau by t, which is the tangential vector. And I know that my value of um, tan alpha should be equal to alpha if the d alpha is quite small. So in that case, I know that this value dl should be equal to r times d alpha, because in this sector, the always we know that when I have a small circle, I could consider this as a circular path because it's quite small, and r times theta should be equal to the length of the arc. The length of the arc here would be dl, and rho is the radius of the circular path at that moment. So rho into d alpha would be equal to dl. In that case, I could define d alpha as dl by rho, and as well from here I could say tan d alpha would be d tau by tau, isn't it? And tau value is 1. Reason being because it is a unit vector, unit tangential vector. So d tau by 1 would be equal to d alpha, which would be equal to dl by rho. From this I can get the value of d tau by dl, which is equal to 1 by rho. So in place of d tau by dl, I could substitute this 1 by rho. So I would end up with the acceleration of this particle in this trajectory as dv tau by dt into tau plus v square by rho n. What is this n? This n is basically the direction here of d tau, which is perpendicular to essentially this, since dl tends to 0, tau 1 and tau 2 will tend to be at the same point, and this d tau is essentially going to be perpendicular to this two directions, right? As you can see here, tau 2 minus tau 1 will be, as it closes to 0, this d tau will tend to be perpendicular to this direction. So it will be basically the radial direction, which I am defining by n. And this n would be the normal vector directed towards the center. Okay, right. So we have understood the three ways of representation, and the three ways, which is, once again, if we can summarize this, the first way is the vectorial method. The second one is the coordinate system method. So in the first case, I define the position vector, and the rate of change of the position vector is my velocity, and the accelerations I could get likewise. In the same way, the second method is I define a coordinate to a given position in space, The third one is the natural method, which is if I know the trajectory of the path, then I could define a tangential velocity vector, and likewise I could get the value of the accelerations and the um, accelerations as well. Now, given an object that is moving in space, it could do two of the things. It could either translate or it could rotate about a stationary axis, and any other kind of motion is essentially going to be a combination of these two, like a plane motion or rotation about a stationary point and a free motion, etc., are going to be basically the combination of these two, right? So if we study the translation and rotation about a stationary axis, we would basically understand the we would break down any motion into combinations of these two. So let's study these two. When we are studying these two, we are going to employ the first method. The first three methods we are talking of are basically for translation. We're going to understand translation first with respect to the vectorial method, coordinate system method, and the natural method. So as we have discussed the three kinds of methods for studying the motion of an object, let's just apply them. So we have seen in JE Advanced there are quite often there are many times questions asked with respect to the so will be shown questions. Uh, just a second. So here we are shown that you have, let's take the first question. So here we are shown two particles A and B, and while they're moving at an angle. Airplanes A and B are flying with constant velocity in the same vertical planes at angles 30, 60 with respect to the horizontal. The speed of A is 100 root meter per second at time t equals to 0. An observer in A finds B at a distance of 500 meters. The observer sees B moving with a constant velocity perpendicular to the line of motion of A. If at t equals to t naught, A just escapes being hit by B, t naught in seconds is. So basically, A as is moving is going in this fashion, and there's an observer at A, and A is traveling at 100 root 3 meter per second. Now with respect to A, what's happening is B is another object that's moving at 60 degrees here, and as you can see, as B is moving with respect to A, how does it look? That is what is the question. So here it is essentially going to be which kind of method should be employed in order to define the motion of the particle B. So as you can see, B with respect to the velocity of B with respect to A would be simply put VB bar minus VA bar. So naturally we are going to, because these are vectors mentioned and the angles mentioned, naturally we move towards the vectorial method of doing the things. So therefore we can find that so therefore we can find Vb minus Va would be the resultant velocity, isn't it? So that velocity would be Vb subtracted with Va. This would be minus Va. So Vb and minus Va, this would be your resultant. Given that since this resultant is going to be perpendicular to the direction line of motion of A, the observer sees B moving with a constant velocity perpendicular to the line of motion of A, right? So that is the this is what is mentioned here. If at t equals to t naught, A just escapes being hit. So initially, initial distance, right, at t equals to 0, the distance is given as 500 meters, which means this distance initially is 500 meters. And from then onwards, if we keep A at rest, B is going perpendicular to A. B starts to move like this perpendicular to A. A is just here, B is moving this way. And what would be his velocity, right? And because A and B are shown to be actually moving with constant velocity in the same vertical planes at 30 and 60 degrees with respect to the horizontal velocity shown, the speed of A is given, and just as the speed of A is given, and both have the same constant velocities. Now you see Vb bar minus Va bar has got a resultant perpendicular to A. What does that mean? Let's just represent this in terms of the Vb vector. I could take the component along Va. Let's choose my axis. My axis would be along Va and perpendicular to my Va. So this is my x, this is my y direction. So my Vb vector also I'll have to resolve along two components, along x and along y. Along x, the component of Vb would be, since x is at an angle of 30 degrees, because x is basically along A, right? So x is at 30 degrees to the horizontal, which means my B vector would be basically at 30 degrees to this x. That means the VB vector, I have to just, the thing with vectors is vector resolution always. I'll just have to subtract these two vectors, right? So therefore I'm resolving VB knowing that its resultant is perpendicular to A. That means its component in the direction of A is cancelling out A, right? Because I know that this angle is going to be 30 degrees, the component of VB in the direction of A is going to be VB cos 30. And that is cancelling out A, which is 100 root 3. So cos 30 is root 3 by 2, which means Vb into root 3 by 2 is exactly cancelling out this. So it should be 100 root 3. That said, my value of Vb will be 200. Now if I know that is 200, then the component of Vb perpendicular to A would be basically Vb sine 30. Alright. So that component will be 200 into sine 30 is 1 by 2, which is 100. So the velocity that is perpendicular to A, that A observes B to be having, will be exactly this component alone, 100. And what is this distance? Given that initially this distance is 500 meters. If this distance is 500 meters, the perpendicular, because this is 30, the perpendicular distance here would be 500 into sine 30, which is 1 by 2, right? Because this is 30, this distance is going to be 500 sine 30. That is going to be 250 meters, which means 250 meters, B or A would see that B would cover this distance in a time equal to distance by speed, 250 by 100, that is 2.5 seconds, alright. So A would see that B would almost touch him at this point, where which would be after a time of 2.5 seconds, alright. Let's take the next question. So here we'll see that there's a rocket moving in a gravity free space. So there's a rocket here and it has got an acceleration of 2 meters per second square. Within this rocket of length 4 meters, a ball is thrown from the left end of the chamber, right, with a speed of 0.3 meter per second. This is 0.3, alright. And at the same time, another ball is thrown from the negative x direction at the speed of 0.2 meter per second. So from here, you throw another ball at 0.2 meter per second. Given that both of them are moving inside the rocket at 2 meter per second square, now the time in seconds when the two balls will hit each other is. So now the entire question is being solved from the frame of reference of this rocket, which is a non-inertial frame. Firstly, because it's a non-inertial frame, both of them will have the same 2 meter per second acceleration acted upon them. Alright, so both would have the 2 meter per second square acceleration, which is the pseudo acceleration that I got to give both of them, A and B. Now once I give that, it is mentioned that the I'm supposed to find the time after which both will touch each other. So now I'm on the frame of reference of this rocket. As I'm solving this, I'll observe that the x coordinate, the equations. Now I'm going to solve this from the coordinate method. As you have seen, the second method we have discussed is the coordinate method. So what is the coordinate method? I'm just interested in knowing the x direction velocity here, which is given as vx, which is given as 0.3 for the first object, and vx for the second object is given as 0.2. But given that this will be I bar directions in the plus 1 plus I direction, this is in the minus I direction because it's in the negative direction. And ax is given as here because both are going to have the same pseudo acceleration, which is minus 2 meter per second square. So minus 2 I cap here. Similarly, ax will be minus 2 I cap. Now because I'm interested in the time of collision, which is essentially the relative velocity of 1 and 2, right? So Vx1 minus Vx2 is what I need to find. And if I find that, that is going to be 0.3 I cap minus of minus 0.2 I cap, which is going to be plus 0.2 I cap. Then minus 2 I cap minus 2 I cap gets cancelled. So the relative velocity is going to be 0.5 I cap. That means the distance it's moving with the relative velocity of these two objects is constant, which is 0.5. And the total distance is 4 meters, which said the time taken for these two objects to meet would be the time taken for this relative distance to end, which is 4 by 0.5, that is 8 seconds, right? Let's take another question. A wire which passes through the hole in a small bead. So there's a small bead here and there's a wire that's passing through this bead, and it is bent in the form of a quarter of a circle. The wire is fixed vertically on the ground as shown in the figure. The bead is released from near the top of the wire. So this is a wire. On the top of a wire, we are releasing a bead. So as I release this bead from the top of a wire, this bead naturally slips and reaches the bottom of the bottom, correct? Now it is we are given a scenario where this is exactly quarter of a circle, which means this angle will be 90. That said, we are asked to find the force it applies on the wire. How much is the force that this applies on the wire? So here we have to consider the motion of this particle. How is this motion? As we see, the motion of this particle is definitely going to be on this wire, correct? So more or less it's the third method that we have to find, which is trajectory is already known. I'm interested in finding the acceleration of this particle now. Because it's mentioned that it's just released from here, that means this particle is going to have, as it is released, we can understand that it will slowly start to slide on it and with an increasing speed, right? So at each and every point of time, it's going to have an acceleration that is tangential to this wire, which we are not very interested in because we are asked to find the force it acts on the wire. And at the same time, it's going to have a velocity v, and this velocity v is tangential and also it is part of a circular trajectory. That means the acceleration of this particle will have two components. As we have seen earlier, the acceleration of this particle will have v tau dv tau by dt in the tau direction or the tangential direction. This is my tau direction, plus we will have v square by rho in the n direction, which is essentially the radial direction inward. So this would be my n direction and this would be my tau direction. So I would have v square by rho acceleration in this direction at any given point of time. So as you can see, because if I draw the free body diagram of this mass is going to have, let's say at a given instance where it makes an angle theta with this vertical, this particular particle is going to have a normal reaction by the wire, and it will have a component of mg, right? Because mg force acts vertically down. If I resolve mg along the perpendicular, because this is theta here with the vertical, this theta is with the horizontal here. We know that uh, if I draw the vertical will also make a same angle theta with this with the perpendicular to this radial direction, right? So if this would be theta, or in other words, since this is theta, this is 90 minus theta, this would also be theta. So the components of mg would be mg cos theta um, along this direction, tangential direction, and mg sin theta perpendicular to this direction, which is along the radial direction. Now, if we observe the free body diagram, we can know that it needs to have a net acceleration of v square by rho towards the center. So, n minus mg sin theta, considering this is my positive y direction, should be equal to minus mv square by r. So which means my value of n which I am interested will be equal to mg sin theta minus mv square by r. So as you can see, the value of initially when theta equals to 90, mg sin theta will be mg, and initially the velocity v will be quite less. But as you go down slowly, the velocity keeps increasing. So what essentially happens is, as this particle keeps going down, the velocity keeps increasing. At this point it will have a maximum value of velocity, and the value of mg will be 0, right? So let us see the value of mv square by r with theta exactly. So at a given theta, we know that using the conservation of energy, m if I use the conservation of energy here, initially the total potential energy, which is mgr, should be equal to, at the next point, the potential energy, which is mg into, assuming this is our 0 for the potential, here the potential energy is mgr. At this position, let's consider this position is the position p where we are interested in. So the potential energy will be mg into, this is radius r, and because this is theta, this would be r sin theta, mg r sin theta plus half mv square. So we are interested in mv square by r. Let's just divide both sides with r, and let's send to the 2 to the other side. So we have mv square by r would be equal to 2mg minus 2mg sin theta. Alright, 2mg minus 2mg sin theta is my mv square by r. If we substitute here, I have the normal reaction n as mg sin theta minus mv square by r, which is 2mg minus 2mg sin theta. So as you can see, this value turns out to be 2mg sin theta minus mg, right? Which is nothing but mg times 2 sin theta minus 1. So this value, up till the time when theta is 30 degrees, the value of mg into 2 sin theta minus 1 would be essentially positive. That means my n normal reaction would be outward. But after theta becomes more than 30 degrees, or theta becomes lesser than 30 degrees, the value of 2 sin theta becomes less than 1, which means after that the normal reaction will be negative, so it will be inward. Now these are the direction. So as you can see, this is the normal reaction by the wire on the bead, right? So up till 30 initially it will be outward, later it will be inward. This is on the wire, by the wire on the bead. Now we are asked to find the force it applies on the wire. So we are asked to find the normal reaction by the bead on the wire. It will be exactly opposite. Initially it will be inward, later it will be outward, right? So initially it will be radially inwards, and later it will be outward. So it's the option 4. So as you have seen, these are basic applications of the motion of the particle in um, in this trajectory in different scenarios where we apply the three methods illustrated as earlier. Usually we find students getting confused over how to approach a given problem. Should they be using the uh, the vectorial method? Should they be using the particle method? How should they do that, right? So these are simple guidelines for us to clearly identify which kind of method to employ and solve the problem. Thank you, everybody. We'll be up with more videos in future.